radio system, point-to-point radio systems for radio recording. In that case, the transmission technique is based on transmission on the H and the V polarization of the electrical field. Okay? So two antennas, or two feeders, one for the H, the other for the V polarization. At the receive side, there are two antennas. One that receives the H polarization, the other one that receives the V polarization. And what happens is that ideally the two fields are orthogonal, so ideally the separation between the two is ideal. That is, there is no interference. But in the practice, due to antennas, or due also to propagation, at the receive side you get something like this. So this is interference. Okay? Signal A, signal B. B is not exactly orthogonal to A. This causes interference of B over A. And of course, also of A over B. And the basic idea is to cancel interference at the receive side. What you get at the receive side is something that you can write as A plus KB. This will be on signal 1. And on signal 2, at the second antenna, you will get A plus lambda B. Okay? This is the model of interference. You see, it is like noise. It is additive. The only difference compared to noise is that you have the same signal also on a second measurement, S2. This can be S1 and this can be S2. On S1 you have 1 plus 2, and on S2 you have 2 plus 1. And this coefficient, they depend on the channel. Suppose by now that there is no noise, only this kind of interference. Well, what you can do at the receive side is very, very easy. Multiply S1 by lambda, multiply S2 by kappa, K, and subtract. This is a very basic signal processing. Okay? And now you get lambda A plus lambda K B minus K A minus lambda K B, which is A by lambda minus K. You see? So simply look to S1 and S2 as two equations into the two unknowns A and B, and solve the linear system to get A and B. For instance, for A you can do that. You see? Now take this will be exactly equal to A. Okay? And make a similar processing for B. This is called the solution of a linear system of two equations into two unknowns, but it is also called interference cancellation. Okay? principle of interfering cancellation. Exactly as it happens with linear system, when lambda is equal to k, we have a problem, because this coefficient becomes equal to 0, and we cannot solve the system. And we see this, just assume that lambda is equal to k. When you try to cancel out one of the two signals, you find a coefficient that of the remaining signal that is so small it becomes 0. And with digital communication, it also happens that there is noise. Okay? The noise is independent on signal 1 and on signal 2, and it is independent of A and B. And so here you will have plus lambda W1 minus K W2. And here you will find 1 over lambda minus K lambda W1 minus K W2 plus A. Okay? That is, add this term here to get the result. This is lambda S1 minus K S2 when there is the noise. You see? So besides A, you also get the noise. Look what happens to the noise term. Okay, if lambda is equal to K, this goes to infinity. These two terms are uncorrelated. So the power here of the sum is lambda to the square by the power 1 plus k to the square by the power 2 divided by lambda minus k to the square. This is the power of the noise, you see? While the power of the signal is the power of A. And so look to this term. When lambda is close to k, the power of this term goes up and up and up. Cancellation is difficult when the system is close to be singular. When the system is a singular, cancellation is impossible. But let us come to singularity step by step. What happens step by step? That the coefficients that you put here, to this, basically this coefficient, as the system smoothly goes to singularity, this term becomes higher and higher. Okay, if there is no noise, no problem. And then at a certain point, when lambda is equal to k, you can no more solve the system. But up to that point, you can solve the system, and you do it. When there is the noise, this happens. The power of the noise after cancellation becomes bigger and bigger as the system becomes closer and closer to be singular, due to this denominator here. Okay? This effect limits the performance, limits the capacity of the channel. That is, the capacity of the channel will depend not only on the signal to noise ratio, but also on the matrix of these coefficients. Okay? Because of a phenomenon like this. There are also cases like this. Look to this case. Here we are lucky because it's enough to make the sum of the two to get 2 times A plus W1 plus W2. So the power of the usable signal is 4 times the power of A, while the power here is 2 times the power of the individual one, W. So you see, in this case, the interference is useful. We have 2 measurements, and when we add them, the interference disappears. So everything goes as if interference were absent. And so we take profit from the 2 measurements, because A is the same here and here, it is correlated. And we have the coefficient 2, and raising it to the square we have the 4. While the 2 noise terms are uncorrelated. So when we add them, we find the noise that has only 2 times the power, not 4 times like this. So the basic question is, what is the capacity of the MIMO channel? How can we compute it? It will depend on the power of A, on the power of B, on the power of the noise, but it will also depend on how the 2 or the multiple equations are combined when we perform interference cancellation. You see? If this is plus, there is no way of extracting A and B. If this is minus, extraction is easy and leads to a gain in the signal to noise ratio. Now this is just the introduction. Now let's go step by step. There are there are some variants. For instance, this single input, multiple output. You have 1 transmit antenna and many receive antennas. This model interference cancellation, this is called the combination. Combining. There is nothing to cancel. There is only 1 signal and many copies of the receiver signal plus noise. And the problem here is to find the optimum set of coefficients for the combination. That will depend on the signal to noise ratio. And there are many systems that are based on the on MIMO. For instance, the Wi-Fi. We don't have here an access point for the Wi-Fi, but anyway, if you look to the access point of the Wi-Fi in the new generation systems, you will find more than 1 antenna. And typically, the antennas are oriented like this in different ways. This leads to diversity. Diversity is very useful in channels that are non-line of sight. This is an example which is typical of line of sight channels. What happens in non-line of sight channel, in mobile channels, in difficult radio channels, it happens that the channel coefficients are time varying, or they depend on the position that you have in the room compared to the antennas. So, by doing this, you increase a lot the chance of having at least one good channel. Okay, because in this case is multiple input, single output. Multiple input, single output. You have many inputs, many antennas with different channels. Channel 1, channel 2. And then you have an antenna here. It is enough that one of these two channels is good to have a good channel between the input and the output. Okay? It is a principle of diversity. This is used also in radio systems with multipath. Suppose that here you have a tower, here you have another tower, and here there is the sea. This system is subject to multipath propagation because of the reflection on the sea surface. Okay, so 1 and 2. These two paths have different delay. And so you can exploit the difference of delay for having diversity between the two. Suppose that one of the two delays is such that, well, look to this channel. Suppose that the delay is such that when here there is the sum between the direct path and the reflected one, they do cancel one with the other. And cancellation depends on the delay. You know, the transfer function, the frequency response of the channel is like this, and this depends on the delay. And if your signal is here, there is perfect cancellation. This other one will have a different delay. And so, in this case, with channel 2, you will have this. And if your signal is here, on the second channel, there will be no cancellation. Okay? This is the principle of diversity, which is an instance of MIMO. As usual, we assume that the channel is known at the receive side. So we know the matrix of the coefficient, and thanks to this knowledge, we can perform combination of cancellation, signal processing that we want to do. Okay? Now let's look to the formal model of the MIMO. We have a vector of input signals, the multiple inputs. That can be A1, A2, AN of Z. A vector of input sequences, because we are in the Z domain. And the channel is represented by matrix H, which is also a matrix of polynomials. And by N. So H, I, J of Z is between AJ and the output XI. So XI, output I of the channel, will be the sum over all the inputs, which is for J that goes from 1 to N, of H, I, J of Z by AJ of Z. This is output I plus noise I. And this is for I equal to 1 to M, the number of outputs. And inputs and outputs. So you can draw a picture like this, AN, and the X1, X2, XM. Between these two, you will have H21, H22, H2N, and the other sum. And the same for all the other outputs. That is, different channel impulse responses and many different, as many are the couples JI, M by N different channel impulse responses. And in the end you have a vector of outputs that can be written as the vector matrix product between channel and input plus the noise vector. So this is the usual model that we have in single input, single output systems, which is extended to the M by N system simply by using matrices and vectors. This is 1 by M M by 1 because it is a column. This is M by N, M by 1, and the size of the noise vector is M, as many, M is the multiplicity of the output, okay? as many noise terms, as many outputs. Questions? It is a linear model. It is simply superposition of effects in time because of the Z, and let's say in the space. This is called the space. The space. It is called space because typically these are antennas that are deployed in different spatial points. Antenna 1, antenna 2, antenna M, antenna 1, antenna 2, antenna M, the transmit and at the receive side. And the Z accounts for the time. In the memoryless case, Hij of Z is simply equal to one coefficient, Hij. This is the memoryless channel. For all the I and J. I equals 1, 2, up to N, and J equal, I up to M, and J equal to 1 to N. If all the Hij's are memoryless, then the assumption on the AWGN is that they are uncorrelated and white, and so the system becomes completely memoryless, and the result is that you can drop the Z. Okay? There is no memory in time because the noise is white, so it has no memory, and the symbol sequence, of course, as always, we assume that it is IID, independent and identically distributed, so there is completely independency between symbols in time and space. And if the channel matrix H do not depend on time, then the system is completely memoryless. And you can analyze it without looking to the time. This is typically in MIMO OFDM. Typical in MIMO OFDM. What happens in OFDM? In OFDM, it happens that carrier by carrier, subcarrier by subcarrier, the channel is narrowband. Okay, so look to the suppose that this is the spectrum of an OFDM system. It is made as the superposition of many subcarriers with narrowband, and which is the model of a narrowband channel. The model of a narrowband channel is memoryless, so that's simply in frequency multiplied by a constant. The output is equal to the input multiplied by a constant, which means memoryless. Problems? Questions? Is it clear? Every time you have a signal X that is A by Y plus W, if this happens in frequency, then this will happen also in time. That is, if you have X of F equal to a constant, let's say K, Y of F plus W of F, you see, when you pass to time, you get X equal to ky plus w. And if this is the input, this is the impulse response of the channel. Simply one tap. Simply a scaling factor. There is no memory induced by the channel. This is the channel. So even if the channel is frequency selective, like this, what happens carrier by carrier is that the bandwidth of that carrier is so narrow that you can consider the channel in the subband as constant. And therefore, frequency by frequency, you have a model like this. This is on frequency 1, let's say. And then you will have the same model on frequency 2 with another value of k. This will be the K1, K2, K3, and blah, blah, blah. But frequency by frequency, each subcarrier is simply scaled by the channel. This is F1 and this is K1. And inside the small bandwidth, you can consider the channel as if it were constant. And if it is constant, so it is ideal. And if it is ideal, it hasn't memory. It is a Nyquist channel, basically. In each subcarrier, you have a Nyquist channel. And what changes between subcarrier and subcarrier is the amplitude of the Nyquist impulse response. But however, you have Nyquist everywhere with different amplitudes. And the different amplitudes are, when you put together the different amplitudes, you get the frequency response of the channel. But then, at the receive side, you make the multiplexing in frequency. That is, you look to the individual subcarriers by the FFT. And when you look to the individual subcarriers, you find a model like this. Frequency by frequency, with different values of k, but anyway. So this is the model that you have frequency by frequency. X is the vector in the frequency. Now, if you look to a MIMO system and you focus on one of the frequency, you get again a model like this, where now the vector x is the vector of the many channel outputs at the same frequency. Questions? Which are the assumptions that we made with this model? That symbols are uncorrelated. The size of this identity matrix is n. Now we will play with the vector and matrices, and I will put a subscript on square matrix to recall the dimension of the square matrix. So this is the identity matrix with the size n by n. And the other assumption is about the noise. W by W, this will be N0 by I, and now the size of the identity matrix is m by m, because we have m outputs, so m samples of noise. So also the noise is uncorrelated in the space, and all the noise terms have the same power, and the same happens with A. So the model is completely memoryless, and also it is memoryless, let's say, in the space, the source and the receive side. This induces the interference. Okay, this matrix H. Now let us study the capacity of channel. That is the capacity that we have when we receive vector x. Study capacity, we use the singular value decomposition of matrix H. Of course, the difficulty is with H, because A and W, the two random variables, are very easy to represent. What puts difficulty is the H, because of the interference. It happens exactly what we have seen at the beginning. It depends on the taps, the coefficients of H, which is the capacity. And so we have to play with H, and we play in this way. Remember that H is M times N. And this is called singular value decomposition, U and V are unitary matrices. It is the property of the unitary matrix M is M to the H is equal to M to the H Hermitian by M is equal to I. This is the unitary M. Okay. Oh, so sorry, as D, this is of course D, the diagonal matrix D. D, whose size is M times N, is non-negative and diagonal. To get this result, which are the features of the two matrices U and V, the columns of U are the eigenvectors of H by H to the Hermitian. The columns of V are the eigenvectors of H to the transposed by H. eigenvalues of h to the transpose, the square root of these eigenvalues are the entries of the diagonal of D. So basically, to perform the singular value decomposition, you must find eigenvectors. Yes, you must build this product and this other product. Then find eigenvalues and eigenvector of this one and this one. The eigenvectors of this one are used to build the columns of U. The eigenvectors of this other one are the columns of V. And if you do this, you find that this matrix D is diagonal, and the entries of the diagonal are the eigenvalues of this one. So D can be like this, and then zeros, or like this, and then zeros. It depends on M and N. D is non-square. U and V are square matrices. D is non-square. It's a rectangular matrix. It is diagonal like this or like this. And the entries here are the square root of lambda 1, the square root of lambda 2, h, this is m, the square root of lambda n. This is for n greater than m, and this is for, so the h is m rows. This is for m. So these m rows. There will be zeros. There will be zeros like this. Lambda 1, lambda 2, lambda n, and then zeros. Okay. Yes. Yes, this is what happens. For m greater than n. There are zeros in the eigenvalues of that product. So you will have m non-zero eigenvalues plus zeros. to this. H by H to the transpose. This will be U D by V, which is H, and then put H to the Hermitian transpose, that is V, D to the H, U to the H. Okay? Now this product is the identity matrix. So this is U, D, D, U. And this is the eigenvalue decomposition. When you multiply D, that contains the square root of the eigenvalues by itself, you get the eigenvalues. A square matrix, M times M, so this will be, this is M times N times M, and this will be M times M. And the M entries of this matrix will be square with lambda 1, lambda 2, lambda M, where the lambdas are the eigenvalues of H by H to the transpose. This is the usual eigenvalue, eigenvector decomposition of that spectral matrix. This is called the spectral matrix of the channel. This is like the matrix matched filter, and this is the spectrum of the channel. This is the usual form, you see? Linear operator and this reversed and conjugate version. This H is transposition, which is like time reversing, and conjugation. So it looks, let's say, like when you make in the time domain H by H star Z to the minus star. Reversal and conjugation. This is what happens in time. Filter and matched filter. This is what happens in space. Matrix and matched matrix. The operation of time reversing is here the operation of transposition. And then this H also induces the conjugation. The columns of U, in this analogy, the columns of U are the sinusoids of the spectrum, and lambda is the power spectral density. This is the analogy between the frequency domain and the linear operation induced by matrix H. This is also the reason why this is called the spectral matrix. And this is called the spectral decomposition. singular value decomposition, spectral decomposition. Questions? Now, using the SVD, we write channel output as U D V to the Hermitian conjugate by A, the input stream, the input symbols, plus W. So this is simply the H. Now let us perform at the receive side the signal processing, which is multiplication of X by this matrix. And let's call this transformation of X, X prime. It is a rotation of X. Of course, this operation does not impact channel capacity because it is reversible. U is a unitary matrix, it can be inverted, so the capacity of X prime is same as the capacity of X. This will be UM equal to the H, UM D V A plus UM to the H by W. Okay? This is the identity matrix because U is a unitary matrix. So this will be D. What is this? This is a rotated version of A. Let's call it A prime. And this is a rotated version of W. It is W prime. This model, X prime, is statistically equivalent to X. Basically, we have made nothing, simply a rotation of the received vector. U is a unitary, meaning that it operates rotations of vectors. Okay? The rotation is such that now we can write X prime I equal to the square root of lambda I A prime I plus W prime I. Entry by entry of this X prime, we have a model like this. So the rotation is basically the solution of that system. Because you see now all the equations are decoupled. Into component X prime I, we have only A prime I. And so the capacity of channel I will be the log 2 of the signal of 1 plus the signal to noise ratio. This is the capacity of the channel after the rotation. Remember that since V and U are unitary, the product V by A is statistically equivalent to A. And this one is statistically equivalent to W. Okay? So you can look to A prime as to A, and to W prime as to W, from a statistical point of view. And so this channel prime, is made as the parallel of as many channels as the number of outputs. These are bits over 2 dimensions. And the lambdas are the eigenvalues of H by H to the transposed and conjugate. So, since W prime is statistically equivalent to W, we have again, for instance, that the expectation of W prime by W prime to the conjugate is N0 by the identity matrix of size M. And the same for A prime. It has the same statistics as A from the point of view of this expectation. So all the channels, all the M parallel channels are independent because there is no interference and the noise is uncorrelated on the M channels. Therefore, the capacity of the M channels is the sum of the individual capacitors, which is the log 2 of the product for I from 1 to M of 1 plus lambda I divided by N0. Which is also the log of the depth of I plus the lambda. This can be regarded as a product of eigenvalues. The product of eigenvalues is the determinant of the matrix. Now, rewind and come back to the channel matrix, because we started from the channel matrix, okay? We want a result that depends on the channel matrix. Here, it depends on the eigenvalues of the channel matrix. Well, now it is quite easy because the determinant of a matrix doesn't change if you multiply on the two sides the matrix by unitary matrices. I plus lambda, and then again U. So take this matrix and rotate it. The determinant doesn't change. This is a rotation. This is the log 2 of the determinant of, make the product U by I by U. It is U by U, and U is unitary, so it is again I. And here you have this, which is a scalar, and then U by lambda by U. U lambda U is the spectral decomposition of H by H to the transposed conjugate. And that's it. This is the result. These are this per symbol, per multiple symbols. This is the answer that we were looking for. Given the signal to noise ratio and matrix H, we compute by this log det formula the capacity of the MIMO channel. Okay? Questions? Look, for instance, to this formula. What does a small eigenvalue means? Small eigenvalue means small signal to noise ratio on that channel, on the sub-channel with small lambda. But the small eigenvalues also means that the matrix, the spectral matrix, is close to singular. When the eigenvalue becomes 0, the matrix becomes singular. And at that point, the capacity on that sub-channel is 0. This happens when you have x1 equal to a plus b plus w1, x2, let's come back to the example that I made at the beginning. Suppose that the two channel outputs are the two channel inputs, a plus b, or if you prefer in this writing, a1 plus a2, a1 plus a2, plus w1 plus w2. You see, basically, in this case, you have only one channel, not two. Cancel by now the noise, and look to the result. You have 2 times the same thing from the two outputs. And this is as to say that you have only one channel. Now, again, forget about the noise. Look only here. Consider this as a linear system and try to extract from x1 and x2 a1 and a2. You cannot. Why? Because the linear system is Hill conditioned. If you now build the matrix of systems coefficient and look to the eigenvalues of that matrix, well, you find that one of the two eigenvalues is a 0. But it is clear. It is clear. Forget about the noise. What do you see? You see only one channel, not two. Because you go to the first antenna and you read one number, A1 plus A2. Then you go to the second antenna with the hope of finding something different, some diversity. If you find something different, you can solve the system. But if you find again the same number, well, it is completely useless, the second antenna. Well, what you really find is the same plus noise. And of course, noise is never of help. Okay? Noise is never of help. This means that basically you have only one channel. And you see this looking to the eigenvalues of the system matrix, which is of the spectral matrix of the system, which is H by H, the complex conjugate. Okay? A very, very important formula, because this is the general form of channel capacity. Of the memory's channel capacity, applied to the multiple input, multiple output channels. You see the number of channels with non-zero capacity is at most equal to the dimension of the output, to m. M is the number of output antennas. Of course, you cannot have more than m different channels at that point. You can have less than m depending on the eigenvalues of the channel spectral matrix. But of course, no more than m. Maximum m. Or by reason, in the case where you have time dependency, then build the spectral matrix in the Z domain in this way. Okay, now come back to the case where there is frequency selective channel or time dispersion, anyway, where the impulse response of the individual channels depends on time. It is the non-memoryless case. In place of H, put H of Z. And then build the spectral matrix as usual. That is Z to the minus star, and here the conjugate and the transposition. This is the extension of the usual single spectrum to the multiple case. And this is the spectral matrix that depends on time now. So each entry of this matrix is a polynomial. Use this into that formula, frequency by frequency. Find the capacity of the multiple channels on frequency 1, on frequency 2, on frequency, what is the last frequency, t to the minus 1, and then make the sum of the individual capacities frequency by frequency, which in the dense case is an integral. Let us briefly analyze the performance of the receiver, of the linear receiver. Is it clear? For each frequency you have a capacity which is the log that at that frequency, and then add over the spectrum. Linear detection means first linear processing and then detection. That is, you get the X from the channel, you make a linear processing, you get the Y, and then you perform detection. And here you have the FA. Linear processing simply means that Y is C, a matrix, by the input. That is, perform interference cancellation, as we said at the beginning. Try to come back from the channel output to the channel input by system inversion. This is C by H by A plus C by W. For instance, for C, you can take the zero forcing matrix. This is the zero forcing. If you put this matrix here, you find H to the minus 1 by H by H by A plus zero forcing. And now I'm going to show you the reason of the name. Okay? This is the identity matrix of size n. This is the reason of the name, zero forcing. It forces to zero the interference. After having multiplied x by c, you find again A plus a noise term. Plus a noise term. So, we know everything about A from the statistical point of view. Now let us characterize the noise. Noise N, we call it N. Okay? Specifically, let us look to the power of N. N by N to the H. This will be the expectation of C by W by WH by C to the H, which is N0 by C to the transposed conjugate, which is exactly equal to N0 by H. H to the minus 1 to the H. This is a spectral matrix. It is Hermitian, its inverse is Hermitian, so we can write that this is H to the minus 1. And you see again here the problem that we can encounter with the small eigenvalues. Look to this one. This is a spectral matrix. Consider the spectral decomposition again. When you rise to the minus 1, if you have some eigenvalues that is a 0, you have a problem. There is noise enhancement. Noise enhancement. Okay? It is exactly the term 1 divided by, I don't remember, lambda minus k, how we called it. It is this minus 1. Leads to terms like this. Noise enhancement with the small lambdas. Remember, this one can be written as N0 by UN lambda M UM to the transpose. It was something like that. I don't remember where it was the H, the conjugation. U lambda UH, yes. No. Well, actually, what we have here is the decomposition of the reversed. So it will be a term like V. Lambda V. But anyway, again we have eigenvalues. The eigenvalues here. Because this is a spectrum.
-1.
To the -1, yes. And this produces the noise enhancement when you find some small eigenvalue. And the noise enhancement brings down the capacity of that subchannel. And this is exactly the same that happens with equalization. When you perform equalization of a spectrum like this, suppose that in the frequency you have a spectrum like this, and you want to perform equalization. The equalizer will have a spectrum like this with a zero forcing. And if there is noise at this frequency, equalizer will make noise enhancement. And here it is the same. You are trying to cancel an interference that is virtually non-cancelable. And to cancel it, you must use big coefficients. And using big coefficients, you multiply the noise by big factors, making noise enhancement. Exactly as with a zero forcing equalizer. One possibility is the MMSE. With the MMSE, you put in place of C you add a term like this to the matrix. So, look, this is the term that you must invert. And the problem arises when this matrix has small eigenvalues. Because when you rise them to the -1, they become large, and then they multiply the noise. Okay? So, with the MMSE, before inversion, you add this term. And at this point, the matrix that you invert is always conditional. It cannot have eigenvalues that go to 0 because of this part. This prevents from noise enhancement. Okay, questions? No questions, so let us recap tomorrow again the last lesson, last class.